So, we will again just want to spend some time so you understand, oh okay, this is how I review a data sheet. I will again reiterate this point, being able to understand a data sheet, being able to read a data sheet and being able to compare different parameters, including electrical parameters, including the size of the package, including the need for external components, including price. All of this, the ability to be able to compare different offerings based on all of these parameters is a huge skill, and it is a must have skill for an embedded system engineer, right. A lot of embedded system engineers tend to focus on the coding aspect, but the hardware aspect that pertains to component selection and hardware schematic and layout is just as important. So, input voltage is 1.4 to 5.5. Now, the DC output accuracy is quoted in two different ways, right. There is the accuracy at 25 degree C, which is plus minus 1%. This just comes down to component matching, and then across temperature the variation is minus 1.4 to plus 1.4. Now, you know, depending on the nature of your application, if your consumer application, then you can say 0 degrees to 85 degrees is my range. If you are operating in a industrial application, you might say 0 degrees to 105 degrees is my range, or if you are operating in a even wider, let us say a military application, you might say minus 55 to 125. This is not rated for military, but the temperature range that you define design for is driven by what is the use case. So, minus 1.4% to 1.4% is the variation when you go across temperature. Now, we did not talk about under voltage lockout. Under voltage lockout essentially says that, you know, when you switch on the power, it is going to ramp up because some capacitor somewhere has to be charged to present the right voltage. Until that node crosses a certain voltage, the LDO will not wake up. That is the definition of under voltage lockout, and depending on whether it is transienting up or transienting down, so transitioning up and transitioning down, the values will be different. So, if Vin is rising, 1.3 is the under voltage lockout. If Vin is falling, it is 1.25. So, below 1.2, if let us say for some reason there is some very sustained glitch and Vin drops below 1.25 for a period greater than the shutdown time, the device will go to 0, right. Or if you shut off the power until Vin approaches 1.25, because again some capacitor is getting discharged somewhere, until that capacitor gets discharged to 1.25, the device will give you a certain output, but once the capacitor goes below 1.25, it will enter under voltage lockout and discharge, right. Line regulation, we talked about line regulation yesterday. It is the change in output voltage when the input voltage changes by 1 volt. So, it is delta V out when V in goes from V in nominal to V in nominal plus 1 volt. In this case, it is only 1 millivolt, and you might recall this, right, that originally when we were looking at a resistive divider, our line regulation was very high, it was almost 500 millivolt, and we said okay, that is a very high line regulation. Now, when we went to a band gap reference where we got very good isolation between this reference voltage and the input supply. So, this voltage was isolated from the input supply. When that happened, the line regulation improved remarkably. In fact, in this case the line regulation is ideal, is 0 millivolt. What they are saying is okay, it is not 0 millivolt, it is 1 millivolt, but then a far cry from the 500 millivolt that we were looking at, right. So, in this case the line regulation is 1 millivolt. The load regulation, which is the degree to which the output voltage changes when I load goes from 0 to max, right, is about 16 millivolt. They have given two different readings. but they have not clarified what the difference is. So, we will say okay, it is either 16 or 25 millivolt, and then they have given a very exhaustive table for the dropout voltage. We are not going to go through this in detail, you already know what the dropout voltage means. So, if for example, your battery minimum is 2.7 volt and you are looking to generate a 2.5 volt supply, then you have to keep in mind that okay, beyond that if my dropout voltage is 300 millivolt, once the supply goes, input supply goes below 2.8, at that point, or maybe we will, let us just make sure we understand dropout properly. So, let us say dropout let us take two different cases. So, let us say case 1, supply voltage which is V in is a lithium ion battery. So, can go from 2.7 volt to 4.2 volt, right, and V out desired is 1.8 volt, right. So, what you would check is okay, is V in minimum minus dropout voltage greater than V out is the question. What is V in minimum? 2.7 volt, dropout voltage is 200 millivolt or 0.2 volt, which is not above, equal to, which is greater than 1.8 volt. So, in case 1 we have no problem, the dropout voltage is very good, and for this dropout voltage we know that even at the lowest value of V in, which is V in minimum, the voltage across between the D and S terminals of that output transistor or the output device is still large enough that there is no risk of that operating like a switch, or that output device operating like a switch. That output device under, in case 1, that output device will always operate like a voltage controlled current source. Now, let us say I have case 2 where V in is still the same, it is a lithium ion battery, goes from 2.7 volt to 4.2 volt. My desired V out is 3.3 volt. Let us say this is my use case, right. Now, what will happen? Now, if V in is greater than or equal to 3.5 volt, then V in minus dropout will be greater than or equal to 3.3 volt, since dropout is 0.2 volt, right. But once V in goes less than 3.5 volt, once V in is less than 3.5 volt, V in minus dropout is less than 3.3 volt. What this means is, in this case, this output transistor or the output device will just function like a switch, right. So, at that point it no longer operates like a voltage controlled current source, it starts to operate like a switch. Now, that is not a problem in itself, it is just, again, you have to think through your application and say, yeah, it is okay for for that small fraction of battery life, I am willing to tolerate it operating from operating in the dropout condition, or operating in a condition where the output transistor essentially works like a switch, right. So, once you know the dropout voltage, this is the analysis you would do. When we come back to calculating efficiency, you will understand why in some cases we might be okay allowing it to operate in the dropout condition. Okay. So, that is the thing about the dropout voltage. Ground current or ground pin current is nothing but quiescent current, and I told you quiescent current, it is important to think about the quiescent current in the context of the role it plays in budgeting for your standby current if you choose to keep this device or this component on at all times. It is very risky to play with shutting off too many power supplies, because then it should not happen that turning back on becomes a problem. So, in many designs people tend to keep the power supplies on. So, it is important to know what the quiescent current is, right. And then we have the shutdown current itself, which is now if you choose to disable the power supply, then it is not going to take 34 microamps anymore, it is going to take only 0.1 microamp. Then there is the power supply rejection ratio, which, like I told you, line regulation, what line regulation is in the DC world, it is a DC parameter. PSRR is the same expression across frequency. The name itself is self-explanatory. It is power supply rejection ratio. So, it is the insertion loss you get from the power supply to the output as a function of frequency. So, 100 hertz, for example, if 100 hertz I had 10 millivolt of noise. What this is saying is that if you have 10 millivolt of noise at 100 hertz on the supply, on the output you will get maybe 2 microvolt of noise or thereabouts, maybe 3 microvolt of noise, right. 20 dB is 10 times lower when it comes to voltage. So, 10 millivolt of noise with 60 dB is 10 microvolt of noise, and then that gets divided by another 3 or so 8 dB. So, it will be about 3 microvolts of noise. So, or 3 microvolt at 100 hertz. So, if I had 10 millivolt of 100 hertz noise or a 10 millivolts of a 10 millivolt tone at 100 hertz on my power supply, input power supply, I will get I do not know if I can write here. So, what this means is, if you have 10 millivolt of 100 hertz tone at V in, 68 dB means you will get about 3 microvolt of 100 hertz tone at V out, right. Now, you can do this same thing for other frequencies as well, right. And one of the things I want to think about is, you have read about Bode plot and how loop gain changes with frequency. It will be interesting for you to think about what causes the PSRR to drop with frequency. They are all related in one way or the other, right. Now, if you have 10 millivolt of 100 kilohertz tone at V in, what this is saying is that you will get about 300 microvolt of 100 kilohertz tone at V out, right, because the PSRR is 40 dB poorer. 40 dB when it comes to voltage is a factor of 100, and so what was 3 microvolt at 100 hertz now will become 300 microvolt at 10 kilohertz for the same, for a similar amplitude tone at these two frequencies at the input, right. So, that is something for you to keep in mind, that PSRR is important in terms of how much isolation do I get between the input voltage and the output voltage as a function of frequency. So, that is PSRR. Then we talked about the enable pins. Noise, let us not worry about for now. What we will, whoops. sorry. Okay, just a few more terms. We have startup time, which is essentially the time it takes for the device to wake up. Now, depending on, I told you that if you do not shut it off, there is no problem because this is always on. So, this voltage is always available. But if you are going to, in your system design, turn off this LDO and turn it back on, you need to know what is the sequence in which the different power supplies come up. That is why the startup time is provided. Then we have the output current limit and the short circuit current. Now, again you might remember that we derived all of these parameters for our very simple circuit of a resistive divider. It's just important for us to know how these numbers line up for our application, so that we can now compare different components. Okay. So, what is also instructive to understand is, okay, now that I know how the voltage performs, or let us say I am interested in load regulation for different temperature conditions, that is available as a plot. So, a data sheet usually has a lot of additional information that, let us say you build the product, you are testing it, suddenly you notice something that is inconsistent. Then what you invariably end up doing is saying, okay, let me open the data sheet for this component and see whether this behavior is explained. Maybe there is a temperature variation that you are surprised by, and then you find out, oh, okay, this is how this component behaves. So, it is important to take the time to review the data sheet to be able to tabulate how the different parameters behave, right. The last thing we should maybe do when it comes to the data sheet is just again, so you might recall that this is almost exact replica of the circuit that we drew, right. It is not very different, maybe rotated by 90 degrees, but otherwise the same, right. So, there is the feedback circuit, and I think I understand the fixed voltage better now. So, what they say is they have different parts for different fixed voltages. So, maybe the LDO is the same, they will just change these resistors depending on the output voltage you want. So, each LDO, so if you buy the 7433 for example, the 7433 is a fixed 3.3 volt output LDO. They have a different 7410, they have a different 7418, which is 1.0, 1.8 volts, so on and so forth, right. So, this resistor, the feedback resistor here, so these resistors are fixed, cannot be programmed. So, if you need a different output voltage, you just pick a different LDO. So, this voltage is Vref. So, here you will get Vref into 1 plus R2 by R1, and they would have already chosen R2 by R1 and Vref to get you 3.3 volt for this specific LDO. Then they have other variations where you can get a different voltage, right. What they have done outside of the things we discussed are they have added a block for current limit. So, I told you that this is like a voltage controlled current source. So, if they detect a short, they will go and regulate the voltage to that voltage controlled current source, so that it does not keep, now if you have a short circuit, this will keep flowing lot of current. This current limit circuit ensures that that current is regulated. That is what the current limit block does. Then they have a thermal shutdown block. Again, you think of it this way, anyway I have a voltage control current source, so I can regulate the amount of current that flows. If no current is flowing, that is pretty much like a shutdown. So, whenever I sense a case where the temperature is high, I just have to go activate the voltage to the voltage control current source. So, this is the control point for the load current. So, what you do with that specific node is what determines how much current flows. So, for current limit you might go peg that at a certain level. For thermal shutdown you will essentially shut off, so you might pull that all the way to supply, so that there is no, the VCCS gets 0 input, so no current flows. And then there is under voltage lockout, where it says until this condition is reached, do not start responding to anything. Other than those three aspects, this circuit is exactly what we drew up, right. You have done some work with op amps earlier in this class, so you think of this amplifier in the middle as some sort of an op amp, right. So, this is the functional diagram for a low dropout regulator, right. Again, not very complicated, but good to understand the way the system is put together. So, when they say 1% accuracy, for example, the variation through these resistors is coming to that caused by the resistors is coming to 1%, right. There is feature description which I am going to ignore. Again, I encourage you at some point to take the time to read a data sheet. It tells you everything you need to know about using that component and invariably gives you a lot of detail about how you make sure that the device is used correctly and what can go wrong, and in some cases how much protection is there in the component. So, any which way you look at it, it is useful to look at, right. Let me just see if there is anything else we want to look at. Maybe the last section that you should pay attention to when you look at a data sheet is the application information. So, in this case they have talked about two things. Now, you might remember that when we earlier in the class, when there was a conversation around stability. So, what you do is you look at a Bode plot and you look at how the gain changes as a function of frequency and how that how the gain behaves as you keep accumulating phase with frequency. Now, depending on the type of compensation you have done, depending on the type of circuit you have, what might happen is that you have a first dominant pole where the gain starts dropping, and then you need to make sure that the gain drops below 1 or 0 dB. 1 in the number system is same as 0 dB, that the gain drops below 1 before the phase accumulates more than 180 degrees, right. You anyway have negative feedback. If you accumulate more than 180 degrees of phase with a gain greater than 1, then essentially you have positive feedback, right. You have positive feedback with a gain greater than 1, which means that the system will start to become unstable, right. So, it is important to ensure that you do not accumulate 180 degrees of phase before the gain has gone below 0 dB, below 0 dB or below 1, there is just two ways of saying the same thing. So, what they are saying here is that the TLV743P device uses an advanced internal control loop to obtain stable operation with the use of input or output capacitors. An output capacitance of 1 microfarad or larger generally provides good dynamic performance, right. Now, the output capacitor has some bearing on the stability, because if the amplifier is dominant pole compensated, then if you keep increasing and the dominant pole is somewhere inside the amplifier, if you keep increasing the output capacitor, then you run the risk of a case where you have accumulated 180 degrees of phase before the gain has fallen down too much, right. So, typically chip suppliers give you a range that you can work with. So, they have said 1 microfarad, maybe 10 is okay, but if you start to put larger capacitors, then you run the risk of making the system unstable. So, for any regulator, for any feedback circuit, for any chip that you use that has an analog feedback system, it is important to understand, okay, now I am loading that feedback system with something, will the stability be compromised, what is the acceptable level of load. So, in that context, it is good to know what the output capacitance is. They have said 1 microfarad, so we will stick with 1 microfarad, right. Then there is more on the dropout. This power dissipation we will ignore, and then they also have a I mean, you ignore the DC-DC converter for now. Then they have the typical application scenario, right, where they have shown that 1 microfarad capacitor at both the input and the output, right. So, this is usually what is there in a data sheet. Again, there is a lot more information, I am not going to go through all of it, but hopefully you got a flavor for how you look at and review a data sheet and extract from it information that is important to you, right. Anytime you do hardware design, component selection is a very critical aspect of hardware design, and it is the data sheet is sort of your most powerful tool to be to help you in component selection. For you to be able to compare an LDO from TI to an LDO from analog devices to an LDO from somebody else, the only tool, the main tool you have is the data sheet, because you are not going to be making a reference board, putting that component, putting different components, running a bunch of measurements. You are not going to have that time to be able to do that. What you want to be able to do is review data sheets from different component suppliers and decide what is the right fit for you, right. So, that is where we will stop with the data sheet, right. But I did not go through every page, as I do not know if that is right to say do that as an exercise. Maybe you should, right. A good exercise would be to take any component. It can be a battery charger, can be an audio amplifier, can be a data converter, can be an LDO, and try to go through the complete data sheet to understand, okay, typically we look only at electrical specifications, because the natural tendency is to look at performance and say, okay, what performance do I get? But the thing is, if you do not deploy it correctly in your system, then you might be beset with so many problems that you might be wondering, I am using all the right components, why is this happening, right. Understanding the limits of operation of the device or the component you choose goes a long way in ensuring that your hardware design is sensibly done, and the data sheet is the biggest tool you have in that respect. So, please take the time to pick any data sheet for a component that if you have a bias towards data converters, then you pick up a data converter data sheet. If you have a bias towards regulators, you pick up a regulator data sheet. If you have bias towards battery chargers, you pick that up. But please take the time to go through a data sheet and acclimatize yourself with, oh, these are all the things that typically get covered in a data sheet. That is a big step you can take towards becoming a good hardware system engineer for embedded system design.